learning representations for nonlinear dynamical systems. And in particular, one of the things that we want to discuss is ways in which we can incorporate sort of prior topological or geometric information in the representation. So let me talk a little bit about sort of the challenges of developing data-driven models. In particular, the basic approach, of course, is there's some dynamical system that you're observing. So you typically will have things like time series data. You may be able to actively probe the system, but for now, let's just think about passive observations that you have of the system. And essentially what you're trying to develop some type of mathematical model so that you can predict something, either some observable of the system that you get through averaging, or to make some prediction of what the model or system rather is going to do in the future. And so in the literature, you can go back to some ideas closely related with principal component analysis, for example, to try to come up with a model, for example, of fluid mechanics. And so one technique widely employed is this principal orthogonal decomposition. So if you had something like airflow over an airfoil, like I'm showing here, one idea to come up with a dynamical model of that would be to simply take your high dimensional flow field. You could think about PIV or a direct numerical simulation. You could try to reduce that to an ODE model or something much more simplified by essentially looking at the directions in which the dynamics vary the most, right? So this is a little bit naive. You would kind of take all of your time series data, which has dynamical information in there, make a big point cloud in basically the function space and do PCA on that. And your principal directions essentially are these principal orthogonal decompositions. For some problem that works well, especially if your key feature for importance is variation, which isn't always the case, of course. So that's been improved in a number of directions. Maybe the most notable one is this dynamic mode decomposition, where the idea there is actually to take the dynamics into account, and you essentially look at the sort of directions in that function space where the dynamics is sort of best captured, and by a linear model. And so that's worked quite well. It essentially boils down to also doing a singular value decomposition similar to POD, but now you have a link between the snapshots in your time series. And that also works well for many problems, but does encounter some major challenges, for example, in that the models that you typically end up with work well, provided the sort of key dynamics can be represented as kind of a superposition of those sort of key dynamic modes that you've learned. So for example, if I had a fluorescence microscopy experiment, all I want to do is track or come up with a model for how a protein or something is diffusing, this would be problematic because that translational motion isn't going to boil down to something that you can simply write as a superposition of a few key modes. So there's also techniques that involve dictionary approaches to describing the dynamics, which have become very popular. Things like the Sandia here, which is a sparse L1 regularized dictionary learning method for the dynamical system. But again, the challenge there is you kind of have to know something about symbolically how to represent your dynamical system, or have good methods for learning that underlying dictionary. So what I want to talk about is ways that we can kind of build on some of the successes in these areas, but really leverage some of the recent emerging tools in the machine learning literature to learn, again, low-dimensional representations of dynamical systems. And also discuss a little bit of how we can incorporate the role of constraints and other invariances that we know in advance about our system. Obviously, in the context of physics, there's quite a bit that we know about the invariances, and we really should utilize that to get more statistical gains out of our data. So, so the approach that I'm going to discuss is, I'm going to discuss kind of two areas. One is going to be operator regression, so ways that we can essentially learn the evolution map without resorting to a dictionary. And then the other thing I'm going to talk about is probabilistic autoencoders, which are a way of kind of regularizing autoencoders to get nice, smooth, ideally continuous representations in the latent space that we can use as a basis for encoding, in some sense, our dynamical system. So it's essentially trying to get at, for a certain class of problems, the challenge of developing nonlinear state space models. Again, let me just summarize real quick. There's a lot of techniques that are out there, and in the interest of brevity, I won't talk too much about them. I'll just mention that you might be tempted to use techniques like recurrent neural networks, which are very promising and interesting for certain problems, like they've been used across the field of language analysis, for example. But one of the issues that comes immediately is that there's no way, or no easy way, I should say, to regularize them so that you will get long-term stable dynamics. In some sense, their generality, while that's a bonus for certain problems, can be a negative for learning dynamical systems in that they have a tendency to fit the data that you give them very well, but don't do such a great job at extrapolating because they're not aware necessarily of that intrinsic dynamical structure that ultimately would be the basis for such extrapolation. So what we like to do is, again, encode things like conservation laws and other types of stability constraints into the learning problem so that we learn models which again have those important qualitative properties so that they have a chance of being stable enough to do extrapolation. So that's one of the key challenges we want to address with these approaches. So the overall idea of what we're going to do is we're going to take our high dimensional dynamical system. Here I'm just showing a particular system which you could think of as a one-dimensional PDE. In this case, this would be actually from the Berger's equation, which is a good benchmark problem. This is showing a reaction diffusion system here. We're going to have the dynamics occur in that latent space representation, and then we'll decode that back to the original observable that you had. And then the idea here is you can then train this pipeline in order to come up with this low dimensional dynamical system here, which has the benefit, if it's low enough dimensional, that often you can get mechanistic insight into the dynamics that you are observing. And the low dimensionality also has the benefit of often stabilizing the system, especially if we combine that with other regularizers. Idea, but the question is, how do you get these different terms in this sort of pipeline? And so the first thing, of course, is you would need some way of representing the dynamical laws. I'll talk a little bit about how to do that using these generalized moving least squares neural networks that we've developed for scattered data. And then I'll discuss how we can do the encoding decoding part, learning these probabilistic autoencoders, which are referred to as variational autoencoders. So that's sort of the overarching idea. And so I'll just tell you a little bit about, a little more detail about some of the ways that we're going to go about filling in some of those pieces in that overarching pipeline. So the idea of generalized moving these squares, I don't have a lot of time, again, to go into the details. So I'll kind of refer you to our recent paper and Python package if you're interested in playing around with that. The idea is if I have some kind of differential equation that I'm trying to learn, let's say I'm trying to learn the evolution of a concentration field, let's just start in one dimensions. What you could do is you can learn the differential operator for the evolution of that system by taking your scattered data that represents that field, representing that in terms of some polynomial space, and then looking at basically the map from the vantage point of how those polynomials would be changed, that polynomial representation would change over the snapshot. And so the idea of generalized moving these squares is no longer requires you to stay within the class of like traditional finite difference methods that are on like a regular uniform lattice. You can kind of figure out a lot of those consistency or polynomial conditions kind of in a way that where this method would automatically kind of satisfy those. If you were, for example, thinking about your traditional numerical analysis of trying to find coefficients to represent something like a derivative operation. So the basic idea is we solve these squares problems. For now, you could just think about this as function evaluation, but this can be generalized to account for more physical constraints. You solve this least squares problem to get a polynomial representation, and then basically the action of the operator is going to be represented by some linear operation on those coefficients. So derivatives obviously could be very easily represented. We can sort of handcraft those. The idea is to put this in a machine learning framework so that we can learn more general linear operators. And with a little bit of work, you can actually extend this also to learn nonlinear operators as well by replacing the linear operation of your coefficients with some general function where you take that function from some function class, for example, using Gaussian process regression or neural networks, which then would allow you to learn things, again, that are nonlinear in nature. And so we've used related ideas in learning PD solvers for basically solving PDs on manifolds. And I won't the details there. I'll just kind of refer you to our recent work on that. But this then becomes a kind of powerful class where we can essentially learn differential operators of PDs using data-driven frameworks. So essentially this QZ that I'm showing here can be represented, for example, by a neural network, and then you plug this whole thing into your favorite loss function, maybe least squares loss, for example, and on the snapshots now you can learn a representation of that evolution. You can further constrain that to have certain nice properties like conservation of mass. You can even do this with certain constraints on this so that you can get stable operators. And I'll refer you to our paper for more details on that. So I think in the interest of time, I won't say too much about these generalized moving least squares, but we've applied them to, for example, develop numerical time step integrators for doing long time evolution, where you're essentially learning the dynamical system over timescales which are larger than the Courant-Fredericks-Lewis numbers so that you can overcome stiffness. This is just showing an example for an advection diffusion problem, for example. So this is just showing a comparison between using a finite volume method, which is guaranteed to preserve the overall concentration, versus techniques such as using a kind of direct numerical discretization, which would be based on something like finite differences. And so you can see that you can start to build in some of that physical and numerical structure, which is often essential for getting good, accurate, and stable results. We've also done this for probabilistic, like molecular level systems, where you then want to upscale to continuum level models for trajectories of Brownian motion and learning evolution of effectively the diffusion equation, but from the particle level models. And of course, as I said before, this can be extended to more general particle level models, where we could also learn nonlinear dynamics. And I'll just refer you to the paper for those details. Okay, so let me talk about autoencoders. And so the idea here is we might not know a lot about the structure of the underlying dynamics, and what we want is a low-dimensional representation of that. Again, this can be used as a tool of kind of having the data self-organize in a way for downstream analysis. And the loss function is going to have these three components. It's essentially going to be based on this Bayesian idea of trying to reconstruct probabilistically the data that you saw in hand. So using the maximum likelihood method over some collection of models. Now, that's of course not a very tractable problem, so we're going to approximate that variationally by what's known as the elbow. And so the idea is basically we're going to learn the encoder, decoder, and potentially even the dynamical map on the latent space by minimizing this energy that I'm showing here, loss function. And this loss function has three components. It's got a reconstruction error. That's how well did the encoder decoder reconstruct the data that I have in hand. This Kullback-Leibler divergence, which acts a lot like the Bayesian prior. And then we're going to have a reconstruction error for when we're talking about dynamical systems, not only in predicting the future step, but also recapitulating the step we had in the past. And then this provides a latent space consistency that allows us essentially to take multiple time steps. So here's a demonstration of this in the context of the Burgers equation. I think I'll skip over some of these details and refer you to our paper for that. What we're doing here is we're looking at the parameterized PDE problem, where we have a collection of initial conditions parameterized from alpha 0 to alpha 1, which is shown up here. And the idea is to try to predict dynamics over that collection of initial conditions using some type of latent space representation, as opposed to solving the PDE directly on a grid. And so there's a well-known Cole-Hop transformation where you can convert the viscous Burgers equation into the diffusion equation. Again, I don't have a lot of time to go into detail on that, but that would be one avenue to try to get a reduced order model. And so we're going to compare against that as a reference. And so let me show you how these variational autoencoder methods work in that context. So if all I did was sort of the standard VAE, this is the latent space representation I would have. It's a bit problematic because what I'm showing here is these arcs are where the data is mapped to, but it doesn't map in a sort of self-consistent way, time step to time step. So that reconstruction error that I showed you is quite essential. If you do that, then the data self-organize very nicely. Here we prescribe the latent space dynamics as essentially just being exponential decay, kind of mimicking what we know from the Cole-Hop transformation. And you see the data gets very nicely organized on these arcs, and now you can take multiple time steps and you get sort of a nice self-consistent stable long-time dynamic. And this is showing now the predictions using something like dynamic mode decomposition. You can see it's quite problematic in predicting the nonlinear dynamics. This is the VAE results. And if we were to do linear VAE, where we have a linear input and output space, we can do a little better, but we still can't quite capture those nonlinearities well. We've also extended this to allow for general topological latent spaces. Again, this is with the aim of having a low-dimensional latent structure. I'll refer you to the paper for those details, but you can propagate through that, and it really helps in getting, again, a nice parsimonious representation. And we've also applied this to constrained dynamical systems where there's interesting constraints in the mechanics. So I think I'll just end there, and if you're interested in trying out some of these methods, we have some software packages that we've developed on this, and you can use those in fairly standard machine learning frameworks. I think that's probably a good place to end things. You can go to our website to download software packages and also related papers. I'd be also happy to talk further about this. Thanks again for joining us today.